Welcome to another episode of AP Calc Live. Hey, Verge.
Hi, Mark. How you doing?
I'm fine.
Good.
All right. So you are at AP Calculus AB, and Verge is in Oxford, Mississippi, and I'm a guy named Mark from Denton, Texas. So
Yeah. And yesterday we talked about how we wish we could just get in our car and drive to go see each other. And we actually have done that before, but we can't go anywhere right now. So we'd like to just look at the map and see that it's not that far apart. Especially because traffic isn't bad in this part of the country if you time it right. In the Northeast, forget it. It's a log jam. Same in LA. And, Houston is pretty bad. Dallas, just avoid it,
that was our roadmap to each other. This is our roadmap to the exam, right?
Oh, clever, Mark.
Yeah, nice segue. If it had been scripted, I would have flubbed it. So that's where we're headed. Right now, we're at mixed bag 5 through 7. Tomorrow, anything goes.
Yep.
And then we're going to look at specific types of FRQs next week and kind of wrap things up. And then we did get renewed for a final week of exam prep and send off, and that schedule's coming. But it will be prescribed.
Mm-hmm.
On May 12th at 2 Eastern, hopefully most of you will be taking an AP Calculus exam, either AB or BC. And we got to use a picture 2 days in a row, so that's nice.
And that's from Dallas, medieval times.
Yeah.
Medieval times. My kids love that place.
So we've done our introductions and banter. We are on to our warm-up soon. And then again, units 5 through 7, so that's picking up at what, analysis with derivatives and into anti-differentiation.
Mm-hmm.
And then we'll wrap up and tell you what's in that Dropbox. It is live. Today is Thursday. I think Verge will have a post-it in a minute. That means Tuesday's key went into the Dropbox this morning. So if you, again, we don't put keys for the circuits up. They're self-checking, but the other documents, we provide something.
And if you did want to pause it and go to that Dropbox and get the materials, that would be great.
I'm sorry, let me bring that back up for you then.
No, that's fine.
I kind of blew through that.
Yeah. Well, we just assume that people have been watching, and I think some people have been watching every single day since we started, but some people are just now tuning in because we're doing a review session. So that Dropbox is the shared folder underneath each video.
I think that takes you straight to the calendar, but from the calendar you can go a level up, or down in the description where it says show more, there's a bit.ly link that takes you to the top level of our Dropbox.
And today in the Dropbox, there's no guided notes page or anything. We're starting with our warm up with example 6 from the end of yesterday's notes. And we are doing a free response question or 2, and we are also doing some work off of a Big 10. All of those are in the Dropbox. So you could download them or look at them. All right, go ahead, Mark.
I was gonna say, I meant to do it when we were on the map. A shout out to a couple people. There's about five of you, AP buddies, that I should be spending the night at a friend's house in Duluth tonight and presenting to some wonderful teachers in Duluth tomorrow morning, and that unfortunately got canceled. So I'm thinking about you guys. So, all right. So warm up. You want to read it? You want me to read it, Verge?
Go ahead. Go ahead.
Okay. In a certain locale, there are 2,345 confirmed cases of a virus. The number of confirmed cases at time t in days is modeled by the function n of t. The rate at which the number of confirmed cases is changing can be modeled by the differential equation dn dt is equal to 336 thousandths times n. Determine an equation for n of t.
All right. So you can pause the screen and make sure that you have that jotted down before we go over it. I do have a joke for you. This joke was sent to me by many different students. So, and actually I think a teacher as well came from her husband. But the question is, what is the derivative of cow?
The derivative of cow. I hope it's amusing.
It's prime rib, of course. All right, I'm going to grab this screen and we're going to go ahead and write this differential equation. So let's see if I can do that.
Yay.
Yes, and there's my Post-it note, so we know what day it is, we know what date it is, and we know what episode we're on.
Also, it's funny, it's the 22nd episode, and probably for about the 19th time when you said you can pause your screen, I actually reached like, oh, I can pause my screen. Oh, right.
I'll pause my screen.
She's talking to the students. How silly.
Okay, so so for this one, we can do this, write this differential equation in a couple of different ways. We could, of course, separate, integrate, solve for C, and then solve for our independent variable, or we could recognize the form that this is in. And I think I would like to really talk about recognizing the form that it's in first. If dn dt, the differential equation, is a coefficient times that n, what this is saying is that the derivative is just the original function of some sort times a coefficient. And there's only really one function that behaves like that, where the derivative is itself. And what function would that be, Mark?
So the amount of stuff you have determines how fast you're changing.
Mm-hmm.
That's an exponential, I believe.
Yeah, it's an exponential. So you could really hop to the final answer knowing that the initial amount of cases is 2,345. And this right here ends up in the exponential because of chain rule. So you could hop directly to the answer that n, or n of t, is equal to this initial amount, 2,345.
Uh-oh. There you go.
Am I good? Yeah, that's somehow that
you
seems to
lagged for a
happen.
second on me.
Okay. So you can hop directly to this form right here if you recognize this derivative. If you don't recognize it and you just want to do a separation of variables, of course you could do that as well, where you have dn divided by n is equal to 0.336t. And we worked on these separations of
DT.
variables. Ooh, jeepers. Thank you, Mark.
You're welcome.
That's why you're here.
I know. And I almost ran
goodness.
out. I actually forgot something I wanted to wear today. I was going to wear a specific ring today. I'll save it for tomorrow now. But I almost left the room. I was like, I wonder if I can leave. I'm glad I didn't.
Don't leave.
I didn't.
Don't leave. I was actually, I mean, I'm not going to say that I don't make mistakes, because I make all the time, but like I was actually kind of anti-differentiating in my head right there is kind of what was happening.
Absolutely.
Because the integral of 0.336 dt is just going to be 0.336t, and then plus that constant of integration. Over here, yesterday, Mark talked about this a lot. We've got, if you have the integral of dx over x, or if you have the integral of dy over y, or the integral of d function over function,
Yeah.
then or whatever, some variable that maybe function isn't the right thing to say, this hopefully we're starting to recognize is going to be the natural log of the absolute value of n. Another thing Mark really talked about yesterday is that to find our C value, we probably want to go ahead and substitute in this initial condition first. So the initial condition n of 0 was given to be 2, 3, 4, 5. So let's see, the natural log of the absolute value of 2,345 is equal to.
It's really close to the combination on my luggage.
I just went like this while I was typing. 2, 3, 4, 5.
Amazing.
This has nothing to do with anything. I just made up the problem when I was writing the notes. I mean, there wasn't any sort of, I'm doing research on this growth rate or this number of people or whatever. So my C value is the natural log of 2,345. And then I would go back to this line here and rewrite. So the natural log of the absolute value of n is equal to 0.336t plus the natural log of 2,345. And then to finish it off, I would have to exponentiate. Absolute value of n is equal to, now this expression right here is such that I can bring this algebraically, this 2, 3, 4, 5 to the front. I don't have to, but e to the natural log of that expression is going to just be that expression. And then with the plus, anyway, algebra.
Yeah, I go look at our 7-8 video if you want to see that done a couple more times,
Yes,
or maybe
definitely.
the 7-7 too.
Especially for those students who are on block schedule and really started their AB calculus in January, please spend some time watching those because they'll be helpful. So which branch do I need to select? I need to select the positive branch, and that would be my final result. But you do these problems, 5 or 8 times, and you start noticing the pattern. You say, well, I don't want to do all this work when I can just recognize the model. And it's not that you're not doing calculus. You are reading this differential equation, recognizing the model, and understanding what goes where when you write the equation.
And
so you are absolutely doing calculus.
yeah, and if you're concerned about what gets credit on the exam or anything, if it was a different relationship, if it wasn't that specific relationship where it was, t divided by, n or something on the end, then you do have to show all this work. But this is actually called out in that course and exam description that you can go find, and there's a link somewhere along the way, so you can just Google AP course and description. But there's a what's called an essential knowledge in there that says if something's proportional to the amount, if the rate of change is proportional to the amount you have, then you can jump straight to this CE to the KT model. So
I think it's 7.8 in our
it
curriculum
is,
exam
yes,
design. Yeah.
it is.
So the next example, well, that was the warm up. But since this is kind of a mixed bag review of units 5, 6, and 7, I really wanted to do this problem with you next. And this is a problem for which we have already done parts A and B. This was a free response question from 2017, and it was about a potato. And this is part C, and you don't even really need at all the context for the rest of the problem. You don't need the stem of the problem to do part C. It was completely independent. And I think that's a good thing to know about how AP Calculus sometimes writes their questions, is that a part could actually be independent of the original given information. It's related because it's about a potato, but I don't need to give you the stem here. We can just launch right in on C. Okay, so this T less than 10, an alternate model for the internal temperature of the potato at time t minutes is the function g that satisfies the differential equation dg dt is equal to negative, and then open parentheses g minus 27, close parentheses, to the 2/3, where g of t is measured in degrees Celsius and g of 0 is 91. Find an expression for g of t, and then based on this model, what is the internal temperature of the potato at time t equals 3? So this differential equation, I must find the particular solution. And then once I do, I need to use that model to figure out an approximation for the time, for the temperature at t equals 3. So this is, I definitely don't recognize this differential equation. So I have to do some work here to separate the variables and integrate and do all that kind of good stuff. So I'm just going to recopy it here so I have enough room. So dg dt is equal to negative, and then in parentheses, g minus 27, close parentheses, to the 2/3. And I know that g of 0 is equal to 91. Okay. So dg divided by, I need to get this g expression over there. So divided by g minus 27 to the 2/3 is equal to negative dt. So separate.
And if you want to slide a 1 in there to make yourself feel comfortable, of course, if you want something to hang your opposite sign on, you can, right?
Definitely. I'm actually going to do a little bit more rewriting here just to kind of show a little bit more. Ooh, I forgot my DG. I live in a college town, and when I hear DG, I always think of the sorority. I don't know why. I'm not a sorority girl, but that I always think DG. So there might be some of you out there, you know exactly what I'm talking about. Okay. So I've got the integral of g minus 27 to the negative 2/3 dg is equal to negative the integral of 1 dt. Well, on this side, on the right-hand side, that's pretty straightforward, especially because put the 1 there for clarity. Well, if I took a derivative and I got 1, chances are that that had to have been t. T is the independent variable here. Maybe there was some sort of a constant. This negative here out front, we would bring it down. Okay, other side a little different. We've talked a lot about U substitution and when you need to use it and when you don't. I personally wouldn't be using U substitution here because my inside function has a derivative of 1 with respect to g. So in that case, I'm just thinking about like something to the negative 2/3 and doing a reverse power rule on it. What about you, Mark? Is that the same for you?
Yes.
Okay, so if I take negative 2/3 and I add 1 to it, I get positive 1/3. And then I have to divide by 1/3, which is the same as multiplying by 3.
And I know a lot of people have figured this out, but I'm going to throw it out there because it's always one of those things where kids see it and it's such an aha moment because you see that fraction in the power rule and you really don't want to screw it up. If you just add the denominator to the numerator, that's your new numerator.
Here?
That 3 plus negative 2. So that's why you get a 1 on top.
Is that true for all fractions?
Yeah, because you're adding 1. So you're adding the denominator over the denominator.
So like if I had something, like if I had, I don't know, x minus 2 is to the 5/4, so it's automatically 9/4.
Right, you just do the 5 plus the 4 plus the 5, and that's your new.
Wow, I
Yeah,
love
see,
that.
it's like one of those things. It's like not that hard to prove, not that, but it's like when someone shows you, you're like, ooh. So.
Yeah, that's exactly right. That's lovely. And I always, here's another thing, which is more like reasonableness of your answer. Whenever I anti-differentiate, I mentally check and make sure 1/3 times 3 is 1, and then g minus 27 to the 1/3 minus 1 is negative 2/3, and then times the derivative of what's inside. So like that's another thing to do as well.
That's usually where I catch my trig mistakes. If I mess a sign up with that.
Like a negative, yeah. You mean a SIG?
It's an SIG, yes.
You never mess up an SINE. Okay. Now I know that G is 91, so T is 0, G is 91. That's the starting temperature of the potato when it came out of the oven or the pot of boiling water or whatever it was. And so I have C is equal to 91 minus 27, which is going to be 64. And now we've said it, if we've said it once, we've said it 600 times. You could really leave this C value like this if you wanted to, but to check the reasonableness of your answer, especially because we're not quite done yet, you really might want to do that 91 minus 27. This is a really pretty little cube root. So 3 times the cube root of 64 is 4, and then you get 12 for your C value. So coming back up into here, I'm going to write, well, I'm going to write it down here actually. 3, open parentheses, g minus 27 to the 1/3 is equal to negative t plus that C value of 12. And it said specifically that we want to find an expression for g of t. That means I need to solve for g. You know, it doesn't need to be presented as an equation, but I do need to isolate the g so that everything's in terms of t. So what would I do? I would divide both sides by 3. G minus 27 to the 1/3 equals negative t over 3 plus 12 over 3, which is 4. Now I'm coming up here. And then I'm going to go ahead and cube both sides. So raise both sides to the 3rd power. So I get
Let's
G
not
minus
expand
27.
that.
Okay, I would have to agree with you there. Wasn't planning on it, but yeah.
I have one student who's not watching because he's in Algebra 2 this year who would expand it. So my Q would have it just for him. But
yeah, and would he expand it correctly or?
Yeah, yes, he would. Yeah, that's why I'd have to have
because he loves binomial theorem.
Yeah. So.
All right, so then now I've got this expression here in terms of t for g, and it's looking good. And then it said, estimate, based on this model, what is the internal temperature of the potato at time t equals 3? So now I need to go ahead and substitute a 3 in here for t. So G is going to equal 27 plus then negative 3 over 3 plus 4 cubed. Again, you can leave it like this, but you know, if you have time, I would somewhere check the reasonableness of the answer. The potato is cooling, so we should get a number that's less than our starting amount of 91, but it's not cooling like into the negatives. That wouldn't make any sense.
They also tell
that
you in
kind
the
of stuff.
STEM, it always has to be higher than 27, right? So.
Yeah. So which the STEM actually
we didn't
did
include it, but back
but,
in the STEM, they did tell you. Yes.
Yeah, assuming you've done the whole rest of the problem, like you're in this problem, like you should be checking for the reasonableness of your answer. So let's see. I get 27 plus 3 cubed. That ends up being 27 plus 27, which is 54. And this was in degrees Celsius. You don't have to put the units there. You can just write the 54. So that would have been worth points. Again, you don't have to put the degrees Celsius, so I'm going to erase it. And then also this would have been worth points. But again, you can stop right there.
Yep.
You know,
okay,
that's fine. I just so you know, I happen to be the question leader who for this problem, and reasonableness of answer, kids checking their calculations would have helped them get a point there because they might have found a mistake that they had made somewhere. And unsimplified, even though we say leave them unsimplified, you really should check if you have time. Okay. And Mark, you're going to do some more stuff for us, right?
Some more stuff. I like that. What's hilarious is I have a folder on my desktop that's called stuff, and it's all documents for this material. All right.
So while he's getting that screen, I just basically did 2 problems from Unit 7, the warm-up, and then also another differential equation. Both of them had only the dependent variable showing. If you think back, one of them had just the n showing on the right-hand side, and the other one was just in terms of g on the right-hand side. Those are challenging differential equations, and it's good to think about those side by side. Mark is going to take a look at some ideas from Unit 6. So this is a go ahead.
I was going to say, this was just, I had thrown this down on the paper while you were talking that you can, this is reasonable too, because when you can scratch off or erase, right? So you can check it and then be like, oh, but don't look at that.
Yeah, that's true.
All right, so we're actually going to steal something from Brian Passwater, who's doing he's half of the team doing the wonderful BC stuff in the mornings. See if I'm following our schedule that I have over here on the side. I am good. This is called a Big 10. I think we've given at least one Big 10 already in the Dropbox, have we not?
Yes.
Okay.
Not this one. We did a differential equation.
Well, yeah. And we're not going to go over the whole one today. We may come back and visit parts tomorrow, but we're going to go through about 5 of these. But the idea is he gives you these 10 numbers up here, and he called it Big 10 because he's in Indiana, and I went to a Big 10 school as well, so it should be 14 numbers, but that's a whole nother issue with bases. But he has this 0 through 9, and as you hit an integer, you just cross it off the list. So if you hit 4 twice, you've made a mistake, maybe both times, maybe one of them. So it's a little bit self-checking.
And if you get an answer like -7 or pi or 3.5, you've also made a mistake. So
that's right.
Yeah.
Like I did get one earlier today because I didn't read well.
Well, I got 2 3s earlier today. I was like, come on, Brian. I had to like go back and figure out my mistake.
Yes, it's all his fault. All right, so I'm going to scoot this up so I have some workspace. Sorry, get this here. And probably going to blur you out for a second. There we go. Just put my camera on top of the page.
So again, this was reviewing Unit 6 a little bit, not every single idea in Unit 6, but some of the highlights.
And we're going to start with D. So if you're taking notes and want to label it, or you can just, if you've printed it out, I encourage you to take notes and then try to do it on your own later. It says the velocity of a particle in meters per second is given in the table above for selected times in seconds. Use a left Riemann sum with the 4 subintervals indicated in the table to approximate the total distance the particle travels in meters over the 8 seconds. So before I start my Riemann sum, because you could jump in with a left Riemann sum and get yourself into some hot water. Because we're trying to find the total distance the particle travels. So we have to reach back and remember, how do we find total distance? Any ideas, Verge?
Yeah, you have to integrate the speed.
Definitely integrating. And you said the speed, but this is
Velocity.
velocity, and speed is the absolute value of velocity. So we are doing this left Riemann sum with the absolute values.
So we care nothing for direction, only for magnitude.
Yeah, and that's really important here on this fourth data point, because our velocity is -1 meters per second, but that means our speedometer would read 1 meter per second. And I'm going to take these equal signs off. I'll be honest, if the reading an equal sign there, we're probably going to allow because you've been asked to approximate it this way, but it's better to do it with an approximation. He said a left-hand Riemann sum. We'll deal with that in a second. First, I'm going to look at my intervals. I've got 0 to 1 is 1 wide, 3 to 1 is 2 wide, 4 wide, and 7 to 8 is 1 wide. So I'm going to grab in my widths. And then I'm going to check one last time because this is the one I goofed up earlier. Actually, it wasn't this problem, but it was a similar idea. Left Riemann sum.
It's amazing how we can read what we want to read.
Yeah,
You know
so
what I
out of
mean?
this 0 and this 2, which one am I going to use?
0.
0.
Because it's on the left-hand side.
And actually, what I'm going to do, this is the way I do it in my class when I do this with chalk or on my Promethean, but it's that width with that height. And then that width with that height, this width and that height, and that last width, not times this height, but times the absolute value of this height, because we're looking at speed. And of course, we've said it like we've said 6 million and 1 times now. You could leave it that way on AP, but 4 plus 2 plus 1 is 7.
And if you're doing these for exercises, like you have it probably right because 7 is one of those Big 10 numbers.
And I didn't keep my key. I was looking to check myself.
What do you think I do at 6 in the morning? I do all these calculus problems.
Oh, there it is. I found it. I had it electronically. I just had to open the window for myself. Yay! That looks good. Yeah. It said, if you go back and read the question, it says to approximate the total distance to travel in meters. So if I ask you, how far did this travel in 8 seconds? And you just say 7, you probably need to indicate units, and it would say indicate units. But this says, how far did it travel in meters in 8 seconds? And you just say 7. I gave you the units, so 7 is fine. Of course, putting the meters doesn't hurt.
Just like the degrees Celsius on the last one.
That's why I always do it. Like if I'm asking a kid, like, how far do you live from school? And if they say 5, I don't know. But if I say, how many miles do you live from school?
They probably were saying 5 minutes because
like, in North America, there's a real good chance, and driving's implied.
Yeah, you wouldn't say how many miles, how many minutes.
Yes. Yeah, it's actually kind of fun. I always talk about songs on your favorite playlist. Is that 5? That's a much longer drive, probably. All right. Because I used to do drives that way. Which playlist am I going to use? All right. So let's talk about E. The graph of a function G is shown above for the closed interval 0 to 4. And I hope that's showing up okay. I know it's a little gray.
It looks fine.
Of the following, which has the greatest value? And this is 1, 2, 3, 4, 5. These are subparts of E. Instead of having parts A, B, C of number 1, you have parts 1 through 5 of E. And the one that has the greatest value is the one we cross off our Big 10. So we're going to find the integral from 0 to 4, the left Riemann sum that approximates 0 to 4 on 4 subintervals, the right Riemann sum approximation over 4, the midpoint, and the trapezoidal. And I'm going to make a mess of this diagram.
You know, you could kind of sketch it out on the side, but you're probably just going to do
I'm just going to draw on it. Yeah, I'm just going to go nuts. Okay. So the actual area is that. The actual bounded area is our integral from 0 to 4. So that's my 1. The left Riemann approximation. So we're looking at left endpoints and 4 subintervals. And there's 4 things here that talk about 4 subintervals. So I'm going to go ahead and draw those subintervals. Just draw some vertical lines here.
And it says of equal length. So we sometimes hear that as uniform width.
Yeah.
Either uniform width or
regular partition. Yeah.
Uh-huh.
All right, and I can't tell if that's actually hitting at 0 since you didn't give me the function, or if it's a little above, but I'm just going to draw a tick mark there for that far left. And
it matters not.
Actually. It does not. Not since the function is uniformly increasing. It does not. All right. So I'm just going to draw what my left rectangles would look like.
And that's a nice visual of what you did in D.
So this is under that, and we're looking for greatest. So this one's gone, right?
Mm-hmm.
And then if we look for the right Riemann sum, now I'm going to do these same endpoints, but now it's the right endpoint of the previous interval. Or sorry, this is a subsequent interval, actually, sorry. And that is over. So this is now in the running. This is over that. So this one's gone. And actually at this point it gets much faster. Because where's the midpoint going to be? Well, I find the middle of each interval.
And that's your height.
And that's going to be under this one. It's going to, let's see, I could probably figure out whether that's an over or under of the actual, but I'm not worried about it. It's a lot closer to the actual than any of the others. And I'm out of colors. We'll come in with navy for the trap, but the trap's going to be the average of the left and the right. It's the triangles. Well, triangles on top of rectangles, right? That's what a trap is.
And that one's a really close approximation to the actual. Yeah. Same with the midpoint. So it's definitely
the mid
not
and the
as
trap
over.
are probably really close to each other. These are right.
Yep.
But that means we have a winner. Number 3.
That's why I had 2 3s earlier, because I knew that one was right.
And now this is not always going to be, it's not always going to work this way. The trap and the mid actually aren't always the best. If this thing's oscillating, you can actually get times where the right or the left might be closer to the actual. That's why we have all these different tools. If we knew which one was best all the time, we'd say use right for this and left for that. But if this function's increasing uniformly, you're going to see a pattern like this. If this shows up on an AP problem, I encourage you to draw it, even if you think you know what's going on, because all it takes is one little hump to screw things up for you. All right. And we were going to skip F and run down to G here at the bottom.
Stay tuned tomorrow for things like F. That looks exciting.
I like those. So for G, we have water. Water is slowly poured into an empty glass. That's false. That glass was full of air. Water is slowly poured into a previously empty glass. The height of the water measured in inches is recorded at selected times in seconds in the table above. Use a right Riemann sum with 4 subintervals of equal length. We've heard that before. Indicated by the data in the table to approximate the values of 1/4 of the integral from 0 to 4 of h at t dt. So again, they're equal length this time. So I'm going to use something that Verge mentioned to me earlier this morning, and now I'll mention to you. Every single interval is 1. So we had that other one in D where we had the irregular widths, right?
Which is honestly more typical on an
way
AP
more
exam.
common, yes. Although last year on AB2 they were regular, but if these were all the same and I have a list that's a sum, what can I do with a common multiple inside a sum?
GCF.
Yeah, that common multiple of each term or let's say multiplier is a common factor.
Yeah, that's what you meant.
So I have this 1/4 out front, right? That's from here. And then I've got this common width of 1. So I'm just going to write, you don't have to label it, but I am going to. And now I'm going to go pull my values. And this is where I read poorly this morning because it asked for a right Riemann sum. So I'm going to use the right 4 values. So this interval's using the right, that interval's right, that interval's right. So I'm bringing in 1, 1.25, 2.75 and 3. And I get, let's see, I'll add these first. I'll see, Verge does the easy first. I do the hard first. Get it
Well,
over
those
with.
are easy because you're going to get a whole number.
That's 4 plus 4 is 8, right?
Yeah.
And you don't want to stop there because you had this 1/4 and 1 hiding out front. And so we end up with 2. And this one I got wrong this morning. While Verge had 2 3s, I did the left Riemann sum on this one because I didn't read it well. And I got a decimal, fortunately, so we knew I was wrong. It did not ask for units. It did not ask you to interpret this, but we're going to. It's good practice, right? This integral, what are the units on the integral?
Well, if you just do the integral from 0 to 4 of h of t dt, you're taking the height, which is, what is that? That is centimeters. Oh, inches, and you're multiplying it by the time. So that integral ends up being inches times seconds.
Inch seconds, right?
Yeah, which is not a unit commonly.
That you would use very often. No, it's like man hours or something like that. Every inch, every second, how many inches are we covering in inch second? No, that's even per. It's different than that. Just it's inch seconds. We'll leave it.
It's just weird.
But we have this 1/4, and where's that 1/4 coming from? Probably.
It's the b minus a. It's the difference in the
which then
limits
is per seconds. So when I do inches times seconds divided by seconds, this is 2 inches. And so this integral is finding the average, height of the water?
Yep.
In inches over the time interval 0 to 4 seconds. So if I was asked to interpret it, that would be my interpretation. And of course, there's various ways to word that differently, but you definitely want to appeal to this time interval. You could say the 4 seconds modeled, but you don't just want to say over any 4 seconds because it's specific to these 4 modeled in the table. So.
Or just say the average height of the water. Like you can't say that either.
Yeah, exactly. Because it was empty for a long time before, possibly. Might have even been full before. Right? All right, H. We're going to do 2 more of these. Unless you want to go ahead and jump into that FRQ that we have in reserve.
No, I think the timing is perfect, and we can do that. We can do that tomorrow. Lead off with that.
So this is the rate in hundreds of people per hour that the amount of people in an amusement park is changing. Yeah. Does that read right? The rate is modeled by the function r of t above. Wow, there's just a lot of phrases in there. Is modeled by the function r of t above, where t equals 0 corresponds to 12 p.m. If there are 300 people in the park at 12 p.m., use a midpoint Riemann sum with 3 equal subintervals to approximate the total number of people in hundreds in the park at 6 p.m. So that's important. So this is actually 3 hundreds of people. Let me make that. So we're starting with 300. We have the rate at which it's changing, and for a while people are coming in, right? And then about 4 p.m. people start leaving, and there may be people coming in, but this is our total change, and we start seeing people leaving, and then at 6 nobody's leaving because I imagine the park is closed. Or there's people that are hiding.
Or the price changes. Sometimes
that's
the price
true.
changes.
That's a really good point. Yeah. For some reason, we're approaching a net change of 0 at 6 p.m. Maybe just trickling out, and a few people are coming late on that discounted price. You're right. Okay, for whatever reason, they didn't ask us to interpret the graph, but there I am. All right, so the total change, or the net change, actually I should say, right, is going to be that integral from 0 to 6 of r of t that I'm going to approximate with a midpoint Riemann sum, 3 intervals. So 6 divided by 3 is usually 2. So there's my intervals. And they're all 2 wide, so I'm going to pull out that common width again.
Sounds good.
And find a midpoint. So at 1, we're not finding the midpoint of the curve. We're not being asked to find the average. We're finding the value of the curve at the midpoint of the interval. So if you're like, but that's not midway up, but it is midway between 0 and 2, and that's what we're looking for. And so at 3, it looks like it's at 1. So I'm going to grab 2 and 1. And then people are leaving during this last 2 hours. And they're actually leaving the fastest at the midpoint. -2. Oh, isn't that nice? Oh, by the way, because there's going to be those people who ask, didn't you just cross those out? And you said if I cross stuff out, the reader's never seen it, and now I haven't shown all my work. They're professional mathematicians. We hire teachers and instructors and college professors for a reason. We know the difference between canceling and crossing out, hopefully.
So Mark, don't forget to
and then this is hundreds of people, right?
But you have to answer the question.
Right. So this is 200s of people, or 200 people, has a net change, but remember we had that origin, right? Had that origin of 3. So there are 500 people at 6 p.m.
Yet another digit that we have not used. So we're in good shape.
Yeah. Which we had used the 3 already, right? So we did with the 3.
Yeah.
And I think at this point you may have used the 2. All right. On to J, our last one on the big 10.
We had used the 2 on the one with the water.
Oh yeah.
So,
so self-checking, always good.
Not J, K.
Oh, thank you. Had it written down right. Just. All right, so here's K. It's this shark tooth or whatever, shark fin, depending on which way you point it. Right? It says the graph of f of x is above. Sorry, my desk space. Use a midpoint Riemann sum with 3 easy for you to say, with 3 equal subintervals to approximate 0 to 6, the integral from 0 to 6 of f of x dx. So again, got my midpoints. Or my intervals actually at 3. This time I'm going to do 2 plus 2 plus just for fun. Except that's going to be at times. So there's my common widths. Find my heights at the midpoint. That's going to be at 2. Of course, I don't have to draw these. I just find it entertaining.
And also, one thing I was going to say is that, like, as you're watching these videos, if you feel like you know how to do it before Mark starts doing it or before I start doing it, it'd be a great idea to just try it for yourself and then see if you're right, since we had just done a midpoint before that. So yeah, and we hadn't used 9 before either. So yay, that one worked out great as well.
Congrats to us.
Hey, Mark, let me ask you a question about that, because I started talking right when you brought in that -1/2. Like, were you estimating there, or do you know for sure that it's -1/2 there?
I don't, because he didn't tell us it was a piecewise function or that third segment's linear. So I was just eyeballing it.
Okay.
On the AP exam, they absolutely would tell you that was linear if it was.
Okay. And then they would expect you to know for sure it's -1/2 because you know what the slope of the line is. And
right. You'd be able to, because I'd be able to read from that it's linear from 4,0 to 6,1. So.
And then you couldn't just eyeball it as
-1, sorry.
Yeah, you couldn't just say like -0.4 or something like that. You'd have to know the exact spot where that was. Okay, good.
Yeah, in fact, way back for the BC kids, they had to pull a value off a graph once where they couldn't, and it was a bound question. So they actually had to say it was less than a certain value.
Interesting.
So they could say, like, I know this is less than 1 or greater than -1 and use that as a bound, but that's BC.
Yeah. Hey, Mark, will you go ahead and show the free response question?
Absolutely.
We always plan more than what we're going to get to, and that teachers listening know exactly what we're talking about. You just get excited and I'm going to get to cover all this stuff. But this is definitely in that shared folder, and I would encourage you to work on it before we start talking about it tomorrow. Tomorrow is going to be a mixed bag review, and this is one that kind of goes to Unit 5 and Unit 6. And it's a really excellent question.
And you
we
may
will,
have seen it. It's in AP Classroom. It's one of the ones that's unlocked for students. So
yeah, so we will work on that tomorrow, but we have an ambitious list of things that we want to cover tomorrow that review all topics. So anything else to say about any of those, Mark, before we close
I
out?
don't think so. We did mention that I want to say we did mention that your oh geez, words and trying to set up my slideshow to share in a second here too. Try to multitask and failing. No, I was gonna say you'd mentioned the rest of the Big Ten is in there. There are some topics we're covering tomorrow, so feel absolutely use your notes. This is review. Try to do them, but if there's a couple where you're like, they didn't talk about this,
There are some
wait till
easy
tomorrow,
ones.
and we may
Yeah.
not talk about it tomorrow, but we'll talk about some of them. So.
And we will talk about them all. I mean, eventually, but on that Big Ten, there's some easy ones that we did not do, and there are some very hard ones that we did not do. So you can definitely try some of those as well.
And
yeah.
this is totally random, but I know this is obscure behind me. It's The Pit of Despair, if that helps you figure out the movie reference, because I know some people, teachers are giving quizzes where they have to identify
I just
the
think it would
background.
be inconceivable that they couldn't get that movie
Yes, I think
reference,
the
Mark.
albino would be the helpful albino would be a reference too, but that's anyway. Thanks for watching. We'll be here
Tomorrow's
tomorrow.
Friday. We got lots of good stuff planned, so come join us.
And if you haven't gotten those links to the Dropbox yet, so there they are. There's our schedule, which you've seen. You can pause on these because we're out of here in a second. But again, thanks for coming. We really appreciate you guys.
Bye.